3i Atlas has company. Astronomers detect a nearly identical comet. V1. That was what set off alarms in observatories around the world when the first measurements confirmed that a second object with surprisingly similar characteristics was crossing space near the solar system. No one expected something like this to appear right now in the full critical phase of monitoring 3i Atlas, but the images left no room for doubt. A new visitor was entering the scene, and its initial behavior showed a coincidence that could not be ignored. What seemed like a simple green dot in the automatic record ended up revealing a pattern that had only been observed in objects originating from outside the solar system. The anomalous speed, the hyperbolic trajectory, and the type of emissions detected in its coma instantly drew the attention of teams specialized in interstellar bodies. Each new reading reinforced the same conclusion. Not an ordinary comet? And the most surprising thing was that, despite being independent, its luminous composition and initial activity were almost a mirror of 3i Atlas. In a matter of hours, the scientific community began to reorganize priorities, redirect telescopes, and extend observation shifts. Having a single interstellar visitor was already a rare event. Having two with similar characteristics in the same period was something completely unprecedented. And what these objects carry with them is not just ice and dust, but real clues about the material that exists in remote regions of the galaxy. That is why this discovery immediately became one of the most important of the year. If you are watching this, get ready because this finding is putting the main telescopes on the planet to work. Before we delve into the astonishing discovery of this second interstellar comet that appears almost identical to 3i Atlas, there are 3 things you need to do right now to engage the global astronomical community. First, please like this video to help spread awareness of this unprecedented pair of interstellar visitors to more observers around the world. Second, subscribe and turn on notifications so you do not miss any of the real-time updates as both objects continue their journey through our solar system. And third, go down to the comment section right now and write Twin Interstellar to join the worldwide registry of everyone following this historic dual event. Please do these 3 things immediately. What we have today is not a simple update on 3i Atlas, but a situation that took even the most experienced teams by surprise. For weeks, the monitoring of 3i Atlas was already generating a considerable amount of information, but the discovery of B1 reorganized all priorities. Astronomers did not expect to find another object with the same spectral signature and dynamic behavior as an active interstellar visitor. But that was exactly what happened. The initial confirmation came from a careful comparison between images from different observatories, analyzing not only the characteristic color of the coma, but also the way solar light excited certain molecules. This is crucial to understand where this object might have come from and whether it really has a nature similar to 3i Atlas. For now, what they know is that both show signs of origin beyond the Oort cloud, which means they were not born in the common regions of the solar system. This coincidence turns the event into a unique opportunity to study extraterrestrial material in 2 distinct versions, but extraordinarily similar. And from here every part of the analysis matters because every new piece of data helps reconstruct what these 2 comets represent for modern astronomy. The confirmation of the object V1 began with something that for most observatories would have gone unnoticed as a simple flash in an automatic tracking sequence. However, in facilities specialized in fast-moving objects, any trace showing anomalous acceleration triggers an immediate review. And that was exactly what happened. The initial record showed a weak brightness point that seemed to move slightly faster than conventional comets visible in the same region of the sky. This type of signal is usually reviewed several times with different filters to rule out digital interference or satellites crossing the image. It was in that detailed comparison where something caught attention. The preliminary spectrum of the object did not match the behavior of traditional comets. The reason was simple. The light it emitted contained an atypical proportion of emissions associated with excited molecules that are not usually seen with such intensity in comets born inside the solar system. When performing the first precise measurement of its trajectory, the teams detected that the angle at which B1 was entering did not correspond to common orbits linked to the Oort cloud or known periodic comet families. Instead of a smooth curve, its line of movement showed an open shape typical of hyperbolic trajectories. The kind that only objects not gravitationally bound to the Sun present. This immediately placed B1 in a category of possible interstellar visitor, something extremely rare, given that only a handful of bodies with this profile have been observed in all history. The relationship between the relative speed of B1 and the gravitational influence of the Sun reinforced this possibility, since the object showed no signs of deceleration compatible with bodies originated in inner or middle regions of the system. As measurements accumulated, an even greater surprise emerged. The detected emissions had a chemical signature very similar to that of 3I Atlas. This did not mean that both were identical, but they did share certain unusual patterns in their coma, particularly in the way solar light excited diatomic carbon molecules. That green glow that has generated so many debates regarding 3I Atlas was also present in B1, although in a slightly smaller proportion in the first observations. This detail prompted scientists to directly compare both datasets to analyze whether the coincidence was simple chance or whether there were deeper elements in common. Meanwhile, large aperture telescopes began to focus on the object to obtain higher resolution images. These new shots revealed that B1 presented a small nucleus surrounded by a compact coma with a trace of activity that varied according to its distance from the Sun. Although not as extended as that of 3I Atlas, the tail showed enough activity to rule out that it was an inert body or an interstellar rocky fragment. The interaction between solar radiation and the volatile compounds of the object showed that B1 contained sublimating ice, a characteristic feature of active comets. Astronomers then began to review databases of objects discovered in recent months to check if B1 could have been recorded before without being correctly identified. However, nothing matched its speed or initial position. This reinforced the conclusion that the object emerged practically unexpectedly in the instruments, possibly due to its reduced size or because its activity was too weak before approaching the Sun more closely. That type of behavior is common in comets coming from extremely cold regions, where they remain inactive for millions of years until solar radiation awakens them when approaching the system. Another crucial point of analysis was the comparison between the speed curve of B1 and that of 3I Atlas. Although the values were not identical, both showed similar patterns when adjusted to interstellar object models. This led several specialists to consider the possibility that B1 could be the object of an ejection similar to the one that may have taken 3I Atlas from its original system. Dynamic simulations of interstellar bodies show that it is entirely possible for multiple objects to be shot out of the same stellar system during gravitational disturbance events such as the passage of a nearby star or interactions with giant planets in formation. Even so, demonstrating a direct relationship between B1 and 3I Atlas will require much more precise data, especially complete spectral measurements that allow identifying the exact proportion of elements present. While measurements continued, something caught the attention of astronomers. The luminosity of B1 was increasing faster than expected as it approached the Sun. This usually happens when certain volatile compounds begin to sublimate in greater quantity, revealing inner layers of the nucleus. Although this increase was not as exaggerated as that recorded in 3I Atlas, it did suggest that the object possessed internal characteristics compatible with active comets coming from extremely cold regions. The analysis of these variations is fundamental to estimate not only the composition of the object, but also its size, density, and degree of erosion. The international scientific community then began to coordinate observations between different wavelengths. Infrared-sensitive telescopes sought to detect heat emitted by the nucleus, while optical instruments analyzed light scattering in the coma. These comparisons are essential to identify whether B1 possesses dust particles similar to those of 3I Atlas or whether its composition presents significant variations. Each of these observations added to the apparently hyperbolic trajectory strengthened the classification of B1 as an object of external origin to the solar system. With each new reading, one idea became clear. B1 was not a common comet and its resemblance to 3I Atlas could not be ignored. Although critical details such as the exact proportion of sublimating gases and the real size were still missing, the coincidences were sufficient to catalog it as one of the most relevant discoveries of the year. The appearance of two potentially interstellar objects with such similar physical features opened the door to an unprecedented amount of comparative studies that could reveal valuable information about the formation of planetary systems in other regions of the galaxy. When scientific teams began to analyze in greater depth the orbital dynamics of B1, one of the first elements that caught attention was the way the object reacted to the gravitational influence of the Sun. Unlike comets coming from the Oort cloud, which usually show gradual deceleration when approaching the inner zones of the solar system, B1 maintained an unusually high speed that did not match classical models. This characteristic aligns with what is expected from an interstellar object, since its orbital energy is not controlled by the gravitational limits of the Sun. This kinematic independence is one of the most reliable features to differentiate a local body from one coming from external regions of the galaxy. It is in these details where specialists found signals consistent with the behavior of 3I Atlas, whose trajectory has also been classified as hyperbolic, indicating that it will not return once it heads back into deep space. While studies on movement deepened, another aspect generated special interest: the way the coma of B1 scattered solar light. Initial analyses had already detected a strong presence of the green glow characteristic of diatomic carbon molecules, but it was in the more detailed comparison where deeper parallels emerged between B1 and 3I Atlas. Both objects showed an emission pattern where the intensity of C2 increased as they approached the Sun, something common in active comets, but with a spectral distribution that is not typical of local bodies. This type of behavior is usually associated with materials that have not been processed for long periods in inner regions of the solar system, suggesting that both B1 and 3I Atlas may have spent millions of years in extremely cold environments before beginning their current trajectories. Researchers then began to contrast the evolution of activity between the two objects. 3I Atlas has shown dramatic variations in its luminosity, changes that have been interpreted as events of intense sublimation or release of surface fragments. In the case of B1, although the scale was smaller, the constant increase in its brightness confirmed that the object was not a passive rocky fragment, but a comet with volatile material capable of being released easily when solar radiation heated it. This comparison allowed establishing that even if B1 is smaller or less active, it shares very similar physical processes, opening the possibility that both come from environments where temperatures and chemical conditions favor the preservation of highly volatile compounds. As more data were obtained, an interesting topic emerged related to the orientation of the coma. Conventional comets usually present an orientation influenced by the solar wind and the relationship between the rotation of the nucleus and its distance from the Sun. In B1, the coma showed a slight distortion that did not fully match what was expected for a small and relatively young body. Something similar had already been observed in 3I Atlas, whose directional activity shape suggested an irregular internal geometry or a highly localized emission source, although it cannot be affirmed that both objects share an identical physical structure. The similarities between gas outflow patterns generated new questions about the type of materials present on their surfaces and the thermal history that both may have experienced during their interstellar journey. Another significant point was the study of the nucleus albedo. Although it is difficult to measure the exact albedo without high-resolution observations, preliminary models indicated that B1 might have low reflectivity, something common in comets composed of dark and organic materials. This same pattern had been observed in 3I Atlas, which strengthened the idea that both objects might be formed by similar compounds, possibly the result of chemical processes in the protoplanetary disks of other stars. The importance of this coincidence lies in the fact that interstellar comets function as capsules that preserve ancestral conditions and materials, offering a direct window into the chemical composition of regions of space that we can never physically visit. As analyses progressed, astronomers began to study the possibility that B1 was subject to a rotation that affected the distribution of its activity. This type of behavior is frequent in comets that have irregular structures or fractures in the nucleus. In the data of 3I Atlas, periodic variations in luminosity had already been detected that were interpreted as signs of rotation. For B1, although the variations were more subtle, the pattern suggested a similar process. This caught attention because it could indicate that both objects, despite their differences in size and activity, may have been shaped by similar dynamic environments before being expelled from their original systems. Meanwhile, ultraviolet and infrared-sensitive telescopes provided new information about the internal composition of the object. Ultraviolet observations revealed the presence of highly volatile molecules that are released at relatively low temperatures, which matches the interpretation that B1 contains very little processed material. In infrared, some instruments managed to record thermal emission from the nucleus, although in a limited way due to its small size. However, even these partial data reinforce the idea that B1 shares certain thermal characteristics with 3I Atlas, particularly in the way surface ice absorbs and releases energy. One of the most important debates among experts was to determine whether this coincidence could be considered evidence of a common origin. Although there is still no definitive answer, several elements support this possibility. Both objects show similar chemical signatures, compatible hyperbolic trajectories and activity levels that match comets that have remained in extremely cold regions for long periods. In addition, gravitational ejection models suggest that a stellar system can release multiple objects at the same time, especially during phases of orbital instability. However, to confirm something like that, complete spectral measurements will be needed that allow comparing with exactitude the proportion of the same compounds present in both bodies. For now, what is clear is that B1 represents a new opportunity to study interstellar processes with unprecedented depth. Having two objects with such similar characteristics allows directly comparing their behavior under the influence of the Sun, something that had never been possible in this way. Each new measurement provides essential pieces to understand how these bodies form, evolve and travel through the galaxy and how this material might be related to planetary formation processes in other stars. As the monitoring of B1 progressed, astronomers began to notice an aspect that surprised even those who have spent decades studying comets. The way the object reacted to the gradual increase in solar radiation seemed to reproduce patterns already known in 3I Atlas, but with an intensity that varied in a controlled and predictable way. This is important because interstellar comets usually show unexpected behaviors due to the lack of thermal history in our system. When an object that has spent millions of years in extremely cold regions approaches the Sun for the first time, it is not rare for it to present sudden outbursts of activity or release of unstable compounds. In the case of B1, the release of gas and dust occurred progressively, a sign that its nucleus might possess a more cohesive or less fractured structure than that of 3I Atlas, whose activity has been characterized by abrupt and sudden changes. The detailed study of the variation in its brightness allowed researchers to estimate the speed at which ice sublimated, as well as the proportion of released particles. This measurement is crucial because it helps determine the type of materials present on the surface and inside the nucleus. The data indicated that B1 contained a mixture of volatile compounds that matched those detected in 3I Atlas, but in smaller proportions, which could mean that B1 is a smaller object or that it has suffered fewer internal alterations during its journey. When analyzing these emissions, it was observed that certain ionization patterns followed a curve similar to that recorded in 3I Atlas, especially in wavelengths associated with diatomic carbon. That spectral coincidence generated special interest because it could be key to identifying whether both objects come from chemically compatible regions outside the solar system. While these studies deepened, an important doubt arose. If B1 was really an interstellar comet, what would be its point of origin? To try to answer this question, astronomers traced its trajectory backwards, mathematically reversing it through time using advanced dynamic models. This method allows imagining the path that the object may have taken before entering the system. Although uncertainties are large due to small gravitational variations that can affect the route of any body, initial results indicated that it came from a region of space away from the galactic plane, which coincides with what has been observed in some previous interstellar objects. This coincidence further strengthened the idea that B1 is not a local body, but a visitor that may have been expelled from a distant stellar system millions of years ago. Another element that caught attention was the way B1 interacted with the solar wind. Conventional comets usually show predictable behavior as the wind drags the ion tail in the direction opposite to the Sun. In the case of B1, although the tail was shorter and less bright than that of 3I Atlas, it followed very similar patterns in terms of orientation and dispersion. This similarity not only reinforces its classification as an active comet, but also allows directly comparing the electromagnetic forces acting on both objects. The analysis of these interactions is fundamental to understand the structure of the tail and to identify the types of ionized molecules that the Sun excites during the process. In the case of B1, small bursts of particles were detected that seemed to respond to variations in the solar wind. Signals that matched those observed in comets with more fragile internal structures or with greater concentrations of trapped gases. One of the most complex parts of the analysis focused on the density and estimated size of the nucleus. Determining the exact size of a comet is one of the greatest challenges in cometary astronomy, since the brightness of the coma can completely hide the nucleus. However, using light scattering-based modeling techniques, researchers concluded that B1 probably possesses a small nucleus, perhaps smaller than that of 3I Atlas. Although this could suggest a lower capacity for activity, the presence of volatile compounds confirms that it is sufficiently stable to form an observable coma. This balance between size and activity causes interest because it may indicate that B1 comes from a region of space where cometary formation processes differ slightly from those that produced similar objects. While these models were completed, attention focused on the possible rotation of the nucleus. In 3I Atlas, periodic brightness variations were detected that revealed that its nucleus is rotating at a relatively fast speed. For B1, although the changes were less evident, slight fluctuations were identified that suggested the presence of moderate rotation. Rotation can directly influence the type of activity observed, since areas exposed to the Sun for longer tend to release more material. In B1, these areas seemed to activate as the days progressed, generating an activity pattern that matched small changes in the orientation of the object. This finding is also significant because it allows comparing the internal mechanics of two interstellar comets under similar conditions. From these data, several research groups began working on models that tried to explain why both objects present such marked similarities. Although it cannot be affirmed with absolute certainty that they come from the same environment, the parallels in composition, behavior, and orbital dynamics are too striking to be considered simple coincidence. One possibility is that both emerged from a stellar system where primordial materials contain particular proportions of carbon, ice, and organic compounds. Another option is that the two were the result of similar ejection processes such as intense gravitational interactions with massive planets or companion stars. Each new observation added one more piece to this puzzle, reinforcing the idea that B1 and 3I Atlas represent a rare opportunity to study not only objects crossing our system, but real fragments of galactic history. The simultaneous presence of both objects also opened the possibility of directly comparing their response to the solar environment. As B1 delved deeper into the system, its brightness increased gradually and small modifications in the shape of the coma became more evident. This provided valuable information about the inner layers of the nucleus, since the most volatile materials tend to sublimate before those more resistant. This sequence of compound release is particularly interesting because it allows reconstructing the thermal history of the object. In the case of 3I Atlas, abrupt changes in its activity have been interpreted as signs of internal fractures or sudden release of trapped materials. In B1 the activity seemed more moderate and controlled, which could indicate a less altered nucleus. The combination of these elements further consolidated the importance of the discovery of V1, since it provided a perfect basis for comparing the behavior of two interstellar comets under the same solar context. The possibility that both shared similar structural or chemical characteristics motivated the scientific community to redouble efforts, expanding observation to multiple light ranges. This international coordination allowed obtaining data that would otherwise have been impossible to obtain in such a short time. The combined vision of these studies revealed that B1 is not only an interesting object in itself, but also an essential complement to better understand the behavior of 3I Atlas and by extension of any interstellar comet that may be detected in the future. With the advance of observations, astronomers began to notice that B1 presented a particularly interesting evolution in the behavior of its coma. Although at first it seemed a diffuse and relatively compact cloud, as the days passed it began to show more defined layers that responded to solar radiation in a very similar way to what was observed in 3I Atlas. That layered structure is not common in all comets, since it depends on the composition and internal distribution of ice. In the case of B1, the formation of these layers could indicate that the comet harbors different types of volatile compounds in separate zones, which coincides with studies of interstellar objects that have preserved very ancient chemical materials without having been exposed to heat for long periods. One of the most analyzed details was the way the density of the coma fluctuated slightly as the object rotated. Although rotation was not yet fully confirmed due to the limited amount of data, variations in luminosity indicated that certain regions of the nucleus began to sublimate when exposed to the sun. This pattern resembled that observed in 3I Atlas, whose activity also presented preferential sublimation zones. These similarities allowed researchers to make deeper comparisons about the nature of the nuclei of both objects. The irregular shape of 3I Atlas had already been documented by high-resolution telescopes, which generated the idea that its structure might be composed of united fragments or an elongated nucleus. In B1, although the shape was still uncertain, the light distribution suggested an irregular surface that also influenced the way gas escaped into space. In parallel, spectra obtained with high-precision instruments revealed that B1 emitted traces of complex organic compounds, including light hydrocarbons that have also been detected in local comets. However, the proportion in which these compounds appeared did not match that of typical solar system comets, which further reinforced its classification as an interstellar object. This peculiar chemical signature caught attention because it provided valuable clues about the environment where the object may have formed. Planetary formation models in outer regions of stellar systems suggest that these organic compounds can be preserved for billions of years if they remain in extremely cold environments, far from the heat of the main star. This coincides with the idea that B1 and 3I Atlas may have spent much of their existence in regions where stellar radiation is minimal. While analyses continued, another aspect emerged: the relative size of the tail. Although the tail of B1 was smaller and less luminous than that of 3I Atlas, its orientation showed clear signs of interaction with the solar wind. This allowed astronomers to measure the speed at which ions were dragged, which is key to understanding the type of materials the comet releases. In B1, the speed of these ions matched that of active but relatively compact objects. This characteristic reinforced the idea that the comet possessed a small nucleus, but with enough volatile compounds to generate sustained activity. The direct comparison with 3I Atlas, whose tail is more prominent due to its higher level of activity, allowed establishing a useful reference framework to understand the behavior of B1 during its approach to the Sun. Another important point of study was the rate of mass loss. To calculate it, astronomers analyzed the amount of dust and gas present in the coma, as well as the speed at which the material moved away from the comet. Although the exact rate could not yet be determined precisely, preliminary values showed that it was losing mass at a rate consistent with moderate-sized comets coming from cold regions. These data are fundamental to estimate the longevity of the object, since very small comets can lose much of their volatile material in a short period of time. However, B1 showed enough stability to remain active for a prolonged period, which allowed observatories to schedule a series of long-term observation campaigns. While these calculations were being made, another interesting factor emerged: the possibility that B1 presented a stratified internal structure. This hypothesis was based on the way certain compounds seemed to be released sequentially as the object approached the Sun more closely. This type of behavior is generally observed in objects that have accumulated layers of ice with different sublimation points. The identification of these patterns is key because it helps reconstruct the thermal history of the object and better understand the processes that influenced its original formation. In the case of 3I Atlas, some observations had already suggested the existence of internal layers with different levels of activity, and showing similar signals led scientists to seriously consider the possibility that both objects could have formed in regions of the same stellar system with similar environmental conditions. Throughout these investigations, the scientific community began to focus on the possibility of making projections about the future behavior of B1. Although the object showed no signs of having a fragile nucleus or prone to fragmentation, interaction with the Sun could generate drastic changes in its structure. In the case of 3I Atlas, incidents have been recorded that suggest possible internal ruptures. V1, although more stable, could experience sudden increases in activity if certain internal layers began to sublimate at the same time. To anticipate these events, simulation models were continuously updated as new observations emerged. The combination of all these elements turned B1 into an object of enormous scientific interest, not only for its rarity as an interstellar comet, but also for the opportunity it presents to compare two bodies of external origin under the same solar conditions. The simultaneous analysis of B1 and 3I Atlas provides an unprecedented opportunity to study how two interstellar comets with similar properties behave, allowing astronomers to build a clearer portrait of the processes that occur in regions far from the galaxy. This direct comparison is one of the most important achievements of modern astronomy, as it offers information that would be impossible to obtain otherwise. As coordinated observations in different light ranges progressed, B1 began to show variations that helped astronomers better understand the physical structure of the object. One of the first conclusions was that the activity of B1 was not completely uniform across its surface, suggesting that the nucleus possesses zones with slightly different compositions or regions where ice is more directly exposed. This pattern became evident when analyzing how the intensity of brightness fluctuated at regular intervals, indicating that the comet might be experiencing moderate rotation. Although the exact rotation speed could not yet be determined with certainty due to the distance of the object, repetitive fluctuations in the coma showed clear signs that the nucleus was spinning on its own axis. This characteristic is common in many comets and helps explain why certain regions seem to activate intermittently. As the object continued approaching the Sun, instruments began to record more pronounced changes in the distribution of the coma. Instead of expanding uniformly, some zones seemed to extend faster, suggesting that the comet was releasing material from specific points on the surface. This behavior resembles what was previously observed in 3I Atlas, whose activity presented especially active regions that drove gas jets with greater consistency. In B1, although the level of activity was lower, the patterns were surprisingly similar, which allowed researchers to begin speculating about the possible presence of internal fractures or natural cavities where ice had accumulated in higher concentrations. These formations can result from processes that occurred during the formation of the comet in its system of origin, especially if it was exposed to episodes of material accumulation in different stages of its development. In parallel with these findings, spectra obtained in the ultraviolet range began to show additional characteristics that further reinforced the classification of B1 as an interstellar object. Among the identified compounds were traces of carbon monoxide, an extremely volatile gas that usually sublimates even in extreme cold conditions. The presence of this compound not only indicates the existence of fresh ice inside the comet, but also suggests that B1 has not been subjected to repeated heating cycles, like solar system comets. In local objects, the presence of carbon monoxide tends to decrease over time due to progressive loss of volatile material. In contrast, in a comet newly arrived from interstellar space, these compounds can be found in large quantities, preserved for millions or even billions of years. The analysis of these emissions allowed deeper comparisons with 3I Atlas. In the data obtained from 3I Atlas, a significant presence of carbon monoxide was observed, as well as other complex organic compounds. In B1, although the concentration was lower, the signals were clearly present. This similarity in the relative proportions of certain compounds caught attention because it could indicate that both objects formed in chemically similar environments. The outer regions of young stellar systems, where temperatures are excessively low, favor the accumulation of these materials in the form of solid ice. If B1 and 3I Atlas emerged in such an environment, they most likely carry with them a chemical composition that directly reflects the primordial environment of the system of origin. While chemical analyses continued, another aspect that began to become evident was the way the comet scattered solar light. The reflectivity of the coma of B1 was relatively low, which coincides with objects containing high levels of dark organic compounds on their surface. This type of material is common in primitive comets and in objects that have not been significantly altered by thermal processes. The presence of dark material helps absorb solar radiation and can influence the speed at which the comet releases gas as it heats up. In the case of B1, this moderate absorption seemed to contribute to the gradual behavior that telescopes were recording. Unlike 3I Atlas, whose brightness had shown dramatic increases, B1 seemed to respond in a more controlled way, possibly due to differences in internal structure or in the distribution of volatile compounds. Another important detail was the analysis of the dust present in the coma. To understand it, astronomers studied the way light scattered when interacting with particles. This technique allowed estimating the approximate size of the dust released by the comet. In B1, the particles seemed to be relatively small, which is typical of newly activated comets. Small particles are usually expelled more easily due to the pressure of the gas released during ice sublimation. This suggests that the comet was experiencing a gradual activation process, exposing increasingly deeper layers as it progressed along its path. This observation coincides with interstellar objects that have never been near a star and that begin to release fresh material for the first time. In parallel, dynamic simulations continued trying to reconstruct the possible point of origin of B1. Although uncertainty remained high, the models showed that the object had probably spent millions of years traveling through interstellar space before crossing the border of the solar system. This prolonged trajectory could have been caused by gravitational interactions with other massive objects or even by the passage of B1 near a moving star. The possibility that B1 was expelled from its system of origin due to this type of interaction reinforced the idea that the dynamic processes affecting comets can occur in any region of the galaxy and not only in the vicinity of the Sun. While astronomers analyzed the trajectory, they also focused on determining the future dynamics of the object. Given that the orbit of B1 showed hyperbolic characteristics, it was almost certain that the comet would not remain in the solar system once it completed its close passage to the Sun. This pattern is common in interstellar objects that usually enter the system at high speed and exit again without being trapped by solar gravity. The fact that B1 followed this pattern further reinforced its classification as an interstellar object and provided observatories with a limited time window to collect data. This urgency prompted several research centers to maximize observation schedules to obtain the greatest amount of information before the comet moved too far away. Finally, the simultaneous presence of B1 and 3I Atlas led the scientific community to consider that we were facing a unique opportunity, the possibility of studying two interstellar objects with such similar characteristics and within the same time period offered a historic occasion to directly compare their physical, chemical, and dynamic properties. These comparisons will not only help astronomers better understand comet formation processes in other stellar systems, but could also reveal important clues about how matter is distributed and evolves in interstellar space. Each new observation added one more piece to the puzzle, consolidating the idea that B1 and 3I Atlas represent an unrepeatable opportunity to explore materials that formed far from the Sun and that preserve crucial information about the earliest moments of remote stellar systems. While B1 continued advancing towards increasingly illuminated regions of the solar system, astronomers began to notice important changes in its level of activity. Although from the beginning there were already signs of ice sublimation, it was during this approach phase when instruments detected a more marked increase in gas production. This increase was not sudden but constant and progressive, a behavior that specialists associated with the presence of internal layers of ice that began to become exposed. This type of evolution is typical in comets that have never before been heated by a star, since their internal structure preserves volatile materials in a primordial state. The fact that B1 presented these characteristics only reinforced its classification as an interstellar object, since comets born within the solar system usually experience repeated approach cycles that alter their surface compositions. The detailed study of gas flow allowed more precise estimates about the porosity of the nucleus, a key parameter to understand its internal structure. In B1, the data indicated that the nucleus material could have a highly porous composition, similar to that of other previously studied interstellar objects. A porous structure facilitates gradual ice sublimation because it allows gas to be released through numerous microscopic channels. This behavior coincides with what was observed in 3I Atlas, whose nucleus also showed signs of extreme porosity. The similarity between both cases aroused special interest in the scientific community, since it suggests that interstellar comet formation processes could produce nuclei with similar physical characteristics, regardless of their size or level of activity. Once analyses confirmed the presence of these porosity patterns, researchers began to study in greater detail the thermal distribution within the nucleus of B1. For this, they used energy transfer models that allow simulating how solar heat penetrates the interior of the comet. These models showed that the porous structure of B1 facilitated heat penetration, which accelerated the sublimation of surface layers. However, they also revealed that internal layers remained relatively cold, which explained why the increase in activity had such a controlled rhythm. This process is also consistent with the behavior of 3I Atlas, whose activity has shown stages of gradual variation before presenting more pronounced increases. In both cases, researchers suspect that the internal structure of these objects is composed of layers that formed in different stages of the development of their system of origin. While these thermal studies were completed, another aspect began to gain prominence: the evolution of the color of the coma. Although from the first records a characteristic greenish glow had already been observed, in this phase of approach to the Sun, the intensity of the color increased slightly. This type of variation is usually due to the increase in the activity of specific molecules such as diatomic carbon that emit green light when excited by solar radiation. These changes in color are extremely useful because they function as direct indicators of the type of material that is sublimating. In B1, the persistent presence of this green emission coincided with what was recorded in 3I Atlas, which reinforced the idea that both objects could share surprisingly similar internal chemistry. If this were correct, it would allow astronomers to study two different representations of the same type of interstellar material. At the same time, telescopes equipped with high-sensitivity sensors managed to obtain more detailed images showing how the coma expanded and changed shape as the comet rotated. These images allowed identifying subtle differences in coma density, which indicated the presence of active zones distributed irregularly over the nucleus surface. This pattern had also been observed in 3I Atlas, whose activity showed regions with more intense emissions due to the shape of the nucleus. Although there was still no evidence confirming a similar shape in B1, variations in coma distribution suggested that its nucleus could have a complex geometry, possibly composed of several regions with different levels of exposure to heat. While these investigations progressed, some study groups began to analyze possible scenarios about the origin of B1. Although reconstructed trajectories still had significant margins of error, several models agreed that B1 could come from an interstellar region where star density was relatively low. These regions usually harbor large molecular clouds where young stellar systems form. If B1 emerged in such an environment, it is possible that its composition directly reflects the chemical conditions of that environment. This type of regions characterized by extremely low temperatures favor the formation of ice and organic compounds that can remain trapped for millions of years inside comets. The interesting thing is that the composition analyses of B1 coincided with what is expected from an object formed in this type of environments. In particular, the relative abundance of volatile compounds such as carbon monoxide and light hydrocarbons suggested an origin in regions where stellar radiation was limited. Comparative studies between B1 and 3I Atlas also began to include evaluations about the density of the dust that both comets released. In B1 the particles seemed small and light, which is typical in newly activated comets. In 3I Atlas, instruments had detected particles of various sizes, which could be due to its higher level of activity. The comparison between both particle distributions allowed astronomers to obtain more detailed information about differences in the internal structure of the two objects. This information is essential to understand why both comets show different levels of activity despite having similar chemical compositions. Finally, continuous observations of B1 allowed the scientific community to project its future behavior with a moderate level of precision. Although the comet continued showing stable and controlled activity, models indicated that it was likely to reach its maximum sublimation point when approaching the Sun even more. This process could reveal internal layers containing even more volatile compounds, allowing astronomers to study materials that have remained frozen since the formation of the object. The opportunity to analyze these materials in two distinct interstellar objects represents a historic advance for modern astronomy, as it offers a completely new perspective on the diversity of comets that exist outside the solar system. With the constant increase in activity in B1, astronomers took advantage of every new observation window to improve the precision of coma and tail measurements. One of the most interesting discoveries emerged when instruments began to record subtle changes in the density of the ion tail. Although the tail was shorter than that of highly active comets, its fluctuations seemed to react immediately to variations in the solar wind. This type of rapid response is characteristic of comets with very fine particles and highly ionosable gases, something that coincides with what has been observed in previously studied interstellar objects. The presence of ions in specific proportions, especially in wavelengths associated with carbon molecules, further reinforced the idea that B1 contained chemical material similar to that of 3I Atlas. This coincidence was not only observed in coma behavior, but also in the way the object responded to changes in the solar environment. While these variations in the tail were analyzed, telescopes equipped with high-sensitivity cameras also recorded an increase in dust scattering. The nature of this dust is important because it can reveal the thermal history of the object. In local comets, dust tends to show more uniform patterns due to repeated solar approach cycles. In B1, in contrast, the dust showed a more chaotic but at the same time very fine dispersion, a sign that the released material was fresh and little processed. This is completely coherent with an object that had never before encountered a significant stellar heat source. The presence of fine and highly volatile particles allowed researchers to conclude that B1 was a primordial comet composed of materials that probably formed during the earliest stages of the stellar system from which it came. In parallel with these studies, new models began to emerge that tried to explain the similarities between B1 and 3I Atlas. From a planetary formation perspective, although both objects showed different levels of activity, their chemical, spectral and dynamic behavior suggested that they could have formed in regions of the same type of interstellar environment. These regions, characterized by extremely low temperatures and high densities of simple organic compounds, favor the formation of ice and dust conglomerates that eventually give rise to comets. If B1 and 3I Atlas formed in similar regions, that would explain why both show spectral emissions dominated by volatile compounds such as diatomic carbon and carbon monoxide. This type of data not only helps understand their composition, but also offers clues about the chemistry of protoplanetary disks around young stars in different parts of the galaxy. While studies on dust and gas composition progressed, experts began to examine in greater depth how solar radiation was affecting the internal structure of the object. One of the most important tools for this type of analysis is the measurement of heat reflected by the coma. Although the nucleus of B1 cannot be observed directly due to its small size, the thermal characteristics of the coma allow estimating the surface temperature of the comet. These measurements indicated that B1 was absorbing a greater amount of solar energy as it approached the Sun, which accelerated the sublimation of surface ice. However, the temperature increase was relatively moderate due to the composition of the object and its possible porous structure. This combination of factors prevented sudden explosions of activity, something that has been observed in comets with more fragile internal structures. The controlled behavior of B1 allowed astronomers to obtain stable data over longer periods, which facilitated the construction of more precise models. While specialists analyzed thermal evolution, they also began to study the possible three-dimensional structure of the coma. Using advanced modeling techniques based on light scattering, they managed to recreate the way gas and dust were distributed around the nucleus. These models showed that B1 had a slightly asymmetric coma, suggesting that its activity did not come from a completely uniform surface. This irregularity could be due to differences in the internal distribution of volatile compounds or variations in rotation speed. Although the data were not yet sufficient to confirm a specific structure, the similarities with patterns observed in 3I Atlas were too clear to be ignored. The possibility that both comets shared similar physical characteristics reinforced the idea that they could have formed in regions with similar environmental conditions. Meanwhile, spectral analyses continued to yield results that caught attention. An important particularity was the presence of certain free radicals in the coma that only form under specific radiation conditions. These radicals are very sensitive indicators of the composition of the object and help determine how the material reacts under solar excitation conditions. In B1, the presence of these radicals coincided with that of primitive comets that have not been affected by repeated heating cycles. In the case of 3I Atlas, measurements had revealed a very similar pattern. This chemical parallel further reinforced the hypothesis that both objects could have comparable internal composition, opening the door to deeper studies on how interstellar comets form and evolve in different zones of the galaxy. While analyses continued, several scientific teams began to consider the possibility of detecting deeper structural changes in the nucleus as the object approached its point of maximum activity. Although B1 seemed stable and showed no signs of fragmentation, interstellar comets can react unpredictably to stellar heat due to the presence of highly volatile internal layers. The possibility that B1 could experience a sudden increase in activity motivated researchers to monitor the object continuously. This vigilance allowed detecting slight increases in coma intensity, possibly indications of the start of sublimation of deeper internal layers. Although these changes were still small, the constant progression of the comet towards warmer regions suggested that new observations could reveal more significant variations over time. The evolution of B1 in this period became a key point for comparative studies between interstellar comets. While 3I Atlas went through phases of intense activity, B1 showed more moderate but equally revealing behavior. The possibility of studying simultaneously two interstellar objects with different levels of activity is extremely valuable because it offers a broader perspective on the physical processes that occur in these bodies. Each new reading contributed to forming a clearer image about the diversity of comets that exist outside the solar system and about how they react when coming into contact with stellar radiation. The accumulation of data reinforced the idea that V1 could be a smaller object with more controlled activity, but equally rich in information about its place of origin. As days passed and constant monitoring of comet B1 continued, astronomers began to delve even deeper into the study of the physical processes occurring inside the nucleus. One of the most important observations emerged when high-resolution telescopes detected slight variations in gas emission at different wavelengths. These variations indicated that deeper layers of the nucleus were beginning to heat up, releasing compounds that had remained inactive until then. This type of transition is characteristic of comets composed of primitive ice formed in regions very distant from their original star. The gradual behavior of the activity reinforced the idea that B1 possessed a highly conserved internal structure that has not suffered repeated heating processes like native solar system comets. These new emissions allowed astronomers to identify additional molecules that had not been detected in the first observations. Among them were traces of carbon dioxide and certain heavy hydrocarbons that are common in young molecular clouds. The presence of these compounds provided more clues about the environment where B1 may have formed. In many forming stellar systems, carbon dioxide freezes on dust particles and is only released when the object experiences a considerable temperature increase. The fact that B1 began to release this material just as it entered warmer regions of the solar system was compelling evidence that we are facing an extremely ancient comet that preserves a mixture of volatile compounds dating back to the earliest stages of its system of origin. Meanwhile, observations made in infrared light began to reveal details about the surface temperature of the nucleus. In B1, the temperature increased slowly, indicating that the comet structure was absorbing solar energy progressively. This behavior is typical of an object with a porous surface or covered by dark dust grains that act as thermal insulation. In comparison, 3I Atlas showed a faster increase in its surface temperature, which could be explained by differences in its internal structure or by the presence of areas more exposed to the sun. This direct comparison allowed identifying that although both objects shared similar chemical features, the way they reacted to the solar environment could be different, probably due to differences in size, internal composition or thermal history? While these thermal studies progressed, researchers also focused on the evolution of the dust tail of B1. Although initially this tail was small, its shape began to change as the object approached the Sun. The lightest particles were pushed strongly by solar radiation, while the heaviest remained closer to the nucleus. This difference in dust behavior allowed estimating particle density and approximate size. The data indicated that B1 mainly released very fine dust, suggesting that the comet had a relatively fresh surface without thick layers of processed material. This characteristic further differentiated it from some local comets that after multiple solar approaches develop a hardened surface crust. In B1, the absence of this crust further reinforced the idea that the object had never before been so close to a star. In addition to studying dust distribution, astronomers began to analyze variations in coma shape. As the comet rotated, the coma shape changed slightly due to material release from specific areas of the nucleus. This type of variation is extremely useful for determining the orientation of the rotation axis and for identifying possible active zones on the surface. In B1, the data suggested that the rotation axis might be slightly inclined with respect to the plane of its trajectory, which would explain why some regions heated faster than others. This behavior coincides with what was observed in 3I Atlas, whose activity also shows preferential zones associated with its shape. Although there was still no direct image of the nucleus of B1, variations in the coma provided enough information to begin building models about its three-dimensional structure. While these studies progressed, another aspect began to gain relevance: the stability of the comet. Many interstellar objects present unpredictable behaviors when heating up, which can generate sudden outbursts of activity or even internal fractures. In the case of B1, initial models suggested that the nucleus was relatively stable and showed no signs of imminent fragmentation. However, astronomers continued to carefully monitor any sudden increase in luminosity or abrupt changes in the direction of the gas jet. The stability of B1 contrasted with that of 3I Atlas, which had already shown episodes of intense activity. This difference allowed scientists to compare how two interstellar comets react to solar heat in different ways, providing a broader view of the possible types of nuclei that exist in interstellar space. In parallel, teams specialized in orbital dynamics began to project the future trajectory of B1 with greater precision. The most recent measurements confirmed that the comet followed a hyperbolic orbit, which means it will not remain in the solar system once it completes its close passage to the Sun. It is most likely that after passing perihelion B1 will head back into interstellar space, continuing its journey for millions of years. This trajectory is completely coherent with what is expected from an interstellar object, since its speed and entry angle into the solar system do not allow it to be trapped by solar gravity. The confirmation of this trajectory further reinforced the importance of obtaining as much data as possible in the limited time available. While the scientific community analyzed these findings, a general consensus emerged. Comet B1 represented an invaluable opportunity to understand processes that until very recently were completely inaccessible to astronomy. The fact that B1 shared so many characteristics with 3I Atlas allowed unique comparisons between two real interstellar objects, something that had never before been possible in history. Each new observation provided details that helped reconstruct the origin, evolution, and behavior of these space travelers that carry materials formed in remote regions of the galaxy. The appearance of B1 not only doubled the amount of data available on interstellar objects, but also significantly expanded understanding about the diversity of materials and processes that can occur beyond the solar system. With progress in research on B1, astronomers began to focus on an aspect that became central to understanding the deep nature of the object: its thermal response as it advanced towards more luminous regions of the solar system. The study of temperature is fundamental because it allows determining not only the speed of ice sublimation, but also the finest characteristics of the material composing the nucleus. In the case of B1, measurements revealed particularly interesting behavior. Although the surface temperature increased little by little, the nucleus remained relatively cold, even colder than expected from a newly activated comet. This discrepancy indicates that the internal material of B1 possesses a significant level of thermal insulation, probably due to a highly porous structure that acts as a barrier against heat. This pattern coincides with what has been observed in other interstellar comets and suggests that B1 has conserved for millions of years an almost intact internal structure. While studies on temperature progressed, researchers began to identify differences in the way various molecules were released from the nucleus. In particular, carbon dioxide and complex organic compounds showed gradual release that increased in phases, which is typical of an object containing internal layers of more volatile material. Solar system comets, due to their multiple solar approaches, usually lose these internal layers and develop more homogeneous structures over time. In contrast, B1 showed a clearly stratified structure, characteristic of bodies formed in interstellar regions where extreme cold preserves almost intact the original mixture of ice and dust. This behavior places the comet in a special category, as it offers a direct window into processes that occurred in the earliest moments of its system of origin. While chemical studies deepened, another aspect began to gain strength: the interaction of the object with the solar wind. Observations made at specific wavelengths showed that B1 responded immediately, even to slight variations in solar wind density. This reaction was observed in the form of small increases in the coma, which seemed to expand briefly when certain gusts reached the object. The sensitivity of the comet to these variations indicates that surface activity was dynamic enough to reflect environmental changes almost in real time. This type of behavior has also been documented in 3I Atlas, whose coma shows fluctuations associated with solar wind conditions. The similarity between both objects reinforces the idea that interstellar comets could share coherent physical properties, regardless of their differences in size and level of activity. While these observations progressed, experts began to study in greater detail the radiation scattered by the comet tail. The dust tail, although relatively small, showed interesting patterns that helped determine the size distribution of expelled particles. Analyses indicated that most dust had an extremely small size, which is typical in comets experiencing their first significant exposure to stellar heat. In B1, this presence of fine dust suggested that surface layers of the nucleus had not yet been altered by previous heating processes. The absence of large particles indicates that the nucleus material could be fragile but at the same time very primitive. This finding also coincides with what was observed in 3I Atlas, where the smallest particles dominated the first phases of activity. As research on the tail progressed, broader questions emerged about the possible composition of the comet interior. Although telescopes cannot directly observe the nucleus of such a small and distant object, spectral measurements allow inferring with precision what type of material might be found in the deepest layers. In the case of B1, the data suggested the presence of more complex organic compounds, possibly the result of chemical interactions that occurred in a dense molecular cloud before the comet formed. These compounds have also been observed in other interstellar objects studied in recent decades, suggesting that complex organic chemistry could be something common in star formation regions. This coincidence not only reinforces the importance of studying B1, but also suggests that the materials it carries could be representative of chemical processes present in different regions of the galaxy. While chemical and thermal analyses continued, another point began to gain relevance among researchers: the possibility that B1 would experience important structural changes as it approached the Sun more closely. Although until then the comet had shown stability, models indicated that sublimation of internal layers could weaken certain regions of the nucleus. In some interstellar comets, this process has led to partial fragmentations or even complete ruptures, although there were no clear signs that B1 was at immediate risk of fragmenting. Experts maintained constant monitoring to detect any change in coma shape, since this type of alterations is usually the first indication of a relevant structural change. The stability of B1 contrasted with that of 3I Atlas, which had already shown episodes of intense activity. This difference allowed researchers to compare two completely distinct behaviors in interstellar comets exposed to solar heat. While observations progressed, some teams began to study the interaction between comet activity and ultraviolet solar radiation. This relationship is especially important because ultraviolet radiation can decompose certain molecules and generate radicals that only form under specific conditions. In B1, the presence of these radicals coincided with what is observed in comets containing extremely ancient material. The detection of free radicals provided additional evidence that the comet was formed by compounds that had not been altered since its formation. In combination with data from 3I Atlas, this observation allowed researchers to build a broader panorama about the atmospheric chemistry of interstellar comets. While these studies progressed, one point became especially relevant: the importance of comet B1 as a scientific tool. The almost simultaneous appearance of B1 and 3I Atlas allowed comparing in real time the activity of two interstellar objects with similar compositions and behaviors. This temporal coincidence is extremely rare and provided astronomers with a historic opportunity to study processes that normally cannot be observed with such clarity. The ability to compare two interstellar objects under the same solar conditions provided a completely new line of study that could transform modern understanding about the diversity and evolution of comets in the galaxy. With the constant advance of observations dedicated to B1, astronomers began to consolidate a much clearer and more complete vision about the scientific relevance of the object, especially in comparison with what had already been learned from 3I Atlas. One of the most important conclusions that emerged in this final phase of analysis was that B1, despite having a more moderate level of activity than 3I Atlas, represented an extraordinarily pure example of an interstellar comet, possibly even more pristine in certain aspects. This was due to the way its activity developed gradually, without the abrupt changes that usually signal internal fractures or events of sudden material release. Its controlled behavior allowed more stable measurements, which provided data of exceptional quality about sublimation speed, the type of released compounds and the way these interacted with solar radiation. One of the most outstanding findings in this last phase was the detection of thermal signals coming from deeper regions of the nucleus. Although most heat remained in surface layers, reflecting the insulating structure of the object, some thermal waves reached internal zones and caused gradual release of compounds that had remained trapped since the formation of the comet. This transition allowed astronomers to identify molecules that are not usually easily detected in early stages of activity. Among these compounds were some complex hydrocarbons whose presence is directly related to extremely cold formation environments, typical of dense molecular clouds. This chemical signature reinforced the idea that B1 was an exceptional representative of processes occurring in remote zones of the galaxy, where young stellar systems are born. While chemical studies progressed, it also became evident that comet activity was experiencing an evolution pattern closely linked to nucleus rotation. Variations in brightness, which previously seemed random, now showed clearer periodicity as the object released gas from specific regions of its surface. Although scientists could not yet affirm with absolute certainty what the exact rotation period was, recorded variations suggested that B1 could be rotating at a moderate speed. This behavior is important because it provides indirect information about internal nucleus stability. An object that rotates too fast runs the risk of fragmenting if its structure is fragile. But B1 seemed to maintain a stable balance between its rotation speed and internal material cohesion. This stability allowed the comet to remain intact, even when approaching regions where solar radiation was considerably more intense. As comet activity increased, changes in tail structure also began to be observed. Although this tail continued to be shorter and less bright than that of 3I Atlas, its evolution provided important clues about the properties of released dust. In particular, analyses showed that the average particle size remained extremely small, implying that B1 continued releasing fresh material coming from internal layers that had never before been exposed to heat. This characteristic is a key piece to understand the history of the comet, since it demonstrates that its internal structure practically preserves intact the chemical conditions of its original environment. For astronomers, this represents a unique opportunity to study materials that could be equal or very similar to those present in the interstellar medium in remote epochs, before the system from which B1 came reached maturity. While these data accumulated, dynamic models used by astronomers began to project with greater accuracy the future trajectory of the comet. Everything indicated that once it completed its approach to the Sun, B1 would resume its path towards interstellar space without being trapped by solar gravity. This typical characteristic of hyperbolic orbits definitively confirmed its interstellar origin. More importantly, models suggested that B1 would maintain a sufficiently high speed to leave the solar system without experiencing a significant decrease in its orbital energy. In practical terms, this means that the comet will continue its journey through the galaxy, possibly without passing near another star again in millions of years. This type of trajectory highlights the extreme rarity of the event that astronomers had the opportunity to study. Two interstellar comets detected in the same historical period, both accessible to detailed observations from multiple points on the planet. The simultaneous presence of these two objects also allowed studying how different levels of activity can arise from comets that, despite having been formed in similar environments, experienced distinct thermal and dynamic histories. While 3I Atlas showed episodes of intense activity, abrupt brightness increases and signs of possible fragmentation, B1 maintained more controlled behavior, suggesting that its internal structure may have remained in a more cohesive state throughout its history. This comparison between both objects provides an extraordinarily valuable perspective on the diversity of structures that can exist among interstellar comets. It not only reveals how the internal physics of these bodies influences their behavior, but also offers fundamental clues about the processes that regulate their formation and evolution in environments that are completely out of reach of human space missions. In the final phase of analysis, astronomers began to consolidate the most important findings that emerged from observations of Comet B1. Among these discoveries, one of the most relevant was the confirmation that the object contained a mixture of materials that faithfully represented the chemistry of the environment where it formed. This mixture included volatile compounds, extremely small dust particles and organic molecules that only form under specific conditions within dense molecular clouds. The presence of these compounds not only confirmed the interstellar origin of the comet, but also provided crucial information about the distribution of materials in regions of the galaxy that cannot be studied directly. B1, like 3I Atlas, became a kind of cosmic messenger carrying information about processes that occurred at vast distances from the solar system. As the end of the observation period approached, an idea began to take shape in the scientific community. The consecutive appearance of two interstellar comets with such similar characteristics was not just a stroke of luck, but a unique opportunity to substantially expand human knowledge about the matter that exists in the most remote regions of space. The fact that B1 showed such a pristine structure and such stable behavior turned it into a fundamental reference for comparison with 3I Atlas, allowing astronomers to establish connections that would otherwise have been impossible to identify. Its simultaneous study opened a new window to understand how interstellar objects form, evolve and travel through the galaxy, becoming one of the most important scientific events of recent years.